We're going to talk about interior point methods. And in particular, this is a story about how we apply Newton's method in order to solve more interesting problems than what we've seen so far, or a different class of problems. Let's recall that one of the main selling points of Newton's method is the speed. So Newton's method in the quadratic convergence regime, which sometimes is called phase 2, requires log 1 over epsilon iterations to obtain an epsilon accurate or an epsilon suboptimal solution. And so far, we've seen this applied to the problem minimize f of x, where f of x satisfies all the required properties. It's strongly convex, smooth, and its Hessian is also Lipschitz continuous. We're going to explore where else we can use the idea of Newton's method and the fact that it converges so quickly. Let's look at a problem that we haven't talked about much, that of linear optimization. So recall that the basic problem in linear optimization is to minimize a linear function subject to linear constraints. And you may have seen linear programs in what's called standard form. We're not going to look at standard form too carefully, but these are equivalent. They're equivalent in the sense that it's possible to write any problem in one form or the other. This doesn't mean that the matrix A is the same on the left and the same on the right. But for now, we're gonna stick with this formulation. There's a huge number of applications of linear programming, even though it looks like a very restricted class of problems. Even though the objective is linear and all the constraints are linear, it can still model a huge number of things. So it models many resource allocation problems. You can model scheduling and routing and many other combinatorial optimization problems. Can be either written exactly with linear programming. Linear programming can be used as a tool to solve them, or they can be approximated using linear programming. Just as practice, let's write down what are the optimality conditions. So x hat is an optimal solution if, we've done this many times, 0 is an element of the subdifferential of f at x hat plus some element of the normal cone at x hat. So that means that what's the subdifferential? It's quite easy. It's just the vector c. 0 is an element of c plus something in the normal cone. So I'll leave this as an exercise. Write down the normal cone at a particular solution x hat. And so let me let x hat, in the first case, let it be an interior point. That's an easy exercise, should be a warm-up. And then let it be a corner point. You'll have to think again, what does it mean for something to be a corner point? And again, you can assume that you have corners for this LP. So that's important to think this through and make sure that you can you know how to deal with a problem like that. Okay, why is it that linear programming is so powerful? Linear optimization, linear programming, I'm using these interchangeably. When its objective function is so easy, it's just linear. So really, linear programming, even though it looks like it is just the easiest possible version of the kind of convex problems that the more general convex optimization, in fact, it has a combinatorial nature. And it has a combinatorial nature because of two properties. One, a solution always exists at an extreme point, if a solution exists. If a solution exists, then there is always a solution at an extreme point. An extreme point is another way of saying corner. And secondly, leads to this point, we can have a huge number of extreme points. And the corners are a combinatorial objects, the corners of a particular polytope. So let's see how many corners can we have. So we're looking at a polytope that has a description AX less than B, just like on the previous page. So if the number of corners, I want to know how many corners could this have as a function of how many facets. So A is an M by N matrix. So that means I have M inequalities in N dimensions. So it turns out that the number of corners could be exponential in M. And a very simple example of this, it could be as big as this. It doesn't have to be. A simple example is just the box. So 0, 1 to the N has 2N inequalities, but it has 2 to the N corners. You can also have the reverse. So I'll leave this as an exercise for you to think about. And not so much an exercise as something that you need to solve, but maybe just as a challenge if you haven't seen this before. So I want the reverse relationship. Find a polytope with an exponential number of facets in the number of vertices. So in other words, I want a relationship that looks like M scales like 2 to the N. No, I guess that's not what I'm saying. Not N, but 2 to the number of corners. And I wrote N because the example that I have in mind, you can find something where the number of corners scales linearly with dimension. So this would indeed be something like n. Okay, so this is why linear programming is so powerful, because it allows us, with an extremely parsimonious way, you just specify a small number of constraints, you can encode something with potentially exponential complexity. And this is why it's used as such an important tool to solve these problems that I listed on the previous page. So how do we solve linear programming? So one way is, of course, projected gradient descent. And the main cost here is not the gradient step. The gradient is very, very easy. The gradient is always equal to c, the objective function. The main cost is in the projection. And in fact, you can see that, let's write down what the projection step is. The projection step requires us to solve, given any particular vector z, it requires us to solve, minimize this quadratic subject to x in the polytope. So this may not seem like the best idea, given that we started out, our main task was to minimize a linear function over a polytope, and now we need to minimize a quadratic function over a polytope for every individual step. But we can certainly try to use projected gradient descent. It's certainly a polynomial time algorithm. The simplex method is another approach. We're not going to go into the details of it right now, but the simplex method searches from corner to corner. And it is definitely one of the leading algorithms for solving linear programming. So simplex searches corner to corner. And it has a particular way of moving from one corner point to another in a way that always improves the solution. So you'll see that both of these problems, both of these methods, 1 and 2, have some kind of combinatorial flavor. The simplex method even more, because it explicitly goes from corner to corner. Projected gradient descent, we have to deal with all the corners in the projection step. So we're still not free from that potential challenge. But simplex even more explicitly focuses on all of these on all of the extreme points. We're going to talk about interior point methods, which try to take a continuous approach, a continuous optimization approach, and in particular try to leverage the speed of Newton's method in order to solve linear programming. So one of the things it's in a way opposite to simplex, which goes corner to corner. The idea is avoid the corners. At first, it's counterintuitive because we know by basic geometry properties that we're going to have an optimal solution at an extreme point. But the interior point method has a different thought, and it's really motivated by computational complexity ideas. So let's write down again the basic linear program. Minimize c prime x subject to ax less than b, or writing this out explicitly, ai transpose x less than bi, I equals 1 to m. Interior point method says, okay, let's transform this problem, and instead let's minimize the function ft of x, where ft is equal to t. I don't want you to confuse t as it's not an iteration counter anymore, it's just a multiple. T times c transpose x minus the sum from I equals 1 to m the log of BI minus AI transpose X. And so let's see what this does. This is my original objective as before, but then what happens over here? So we can see that as AI transpose X approaches BI, this becomes log of 0, which goes to minus infinity. So minus log of BI minus AI transpose X goes to plus infinity. This is called a barrier function because it doesn't allow us to even approach the barrier. And so it does not allow us to approach the barrier. But nevertheless, it's also straightforward to see that as t goes to infinity, C transpose xt should approach C transpose X star, the optimal solution. And why is that? And that's simply because as t goes to infinity, you care more and more about this first term compared to the barrier. So you're willing to incur a penalty in order to do something better. So the picture is as you imagine it. Here are my constraints, ax less than b. When t is equal to 0, I start at some point that's, I'll draw it as the center point, but some point that's far from all of the constraints because you're trying to balance this log term. And then as t grows, we follow what's called the central path, and we get closer and closer to X star. So it really is opposite of simplex in every way. It avoids all the corner points. In fact, it never gets exactly to a corner point. But at the same time, you can see that at every single step, all we're doing is solving an unconstrained convex problem. Let's just check convexity. And indeed, ft of x, so let me write this down, at each step, or at each iteration, we solve minimize ft of x to get the solution xt. So this is just a convex problem. Its negative log is convex, so it's convex. It's linear plus convex, which is convex. So this is the idea of interior point method. And I showed you the application to linear programming, but it has many other applications. Perhaps one of the leading areas where we apply interior point methods is to a class of convex optimization problems called semi-definite optimization. And semi-definite optimization is no longer has corner points, so we can't exactly replicate simplex in the same way. So let me tell you quickly what semi-definite optimization is. It's semantically very, very close to linear programming, but it is a much more flexible class. You can express many more optimization problems as semi-definite optimization problems. At the same time, it is much more restricted than general convex optimization. We always have this trade-off. The more restricted your class is, the more you can design specialized algorithms to solve it. So let's first define what semi-definite optimization is. So remember, if I have two matrices, if I have two matrices, A and B, that are in, remembering some of our notation here, that are symmetric, n by n symmetric matrices. Remember that if A is in Sn plus, in particular, that means that all of its eigenvalues are greater than or equal to 0. And sometimes I'll denote this by this curly greater than or equal to sign. And this induces an ordering. So we can say that A is bigger than B exactly if A minus B is bigger than 0, and now we know what that means. So in other words, exactly if A minus B is an element of Sn plus. It has non-negative eigenvalues. So we can use this idea to just replace wherever we had inequality in linear programming. So in linear programming, we have things like AX less than B. So what we really mean here is B minus AX is greater than 0. But what we really mean here is that B minus AX is an element of the positive orthant. So now you see you have a general paradigm, semantic paradigm, whereby I can just replace this positive orthant with something else, with any other cone. That gives you general conic optimization. But in our case, we're going to replace that with membership in the set of positive semi-definite matrices. So what we're going to write down is going to look a lot like a linear program. SDP is minimize C transpose X. I'm going to write this out, just write the coefficients out explicitly here, but this is exactly what we've been writing out in this lecture. Subject to, now I want to write something like AX less than B, but I need to be a little bit more careful. And remember, AX less than B is just AI transpose X less than BI. So this is what I want to mirror. And I'm going to write it, and I'm going to write it as the sum of A. Actually, yeah, apologies. This is not exactly how I wanted to write it. What I wanted to write is that this is equal to the sum of the columns times xj is less than b. I didn't want to write out the rows. I want to write it in terms of the columns. This is what I'm mirroring now. So the constraint I'll write is sum of ai times, we can write aj here, times xj is less than b. So xi is a scalar because x is a vector. A is an n by n matrix, and B is an n by n matrix. And therefore, this inequality defined with respect to the semi-definite cone makes sense. And you can see, you can check that similarly to how we wrote the standard form LP, there are many other ways that you can write SDPs. One other way is minimize sum of Cij Xij. Again, just because there's a C, I'm just reusing the letter. I'm not saying that it's the same C. Just like on the previous page when we wrote down an LP and wrote down in standard form. Subject to, and by the way, this is equal to the trace of C transpose X, where now C is an n by n matrix and X is an n by n matrix. Trace of A L transpose X equals to BL. A is an n by n matrix, BL is a scalar, and X positive semi-definite. So this mirrors the formulation minimize C transpose X subject to AX equals B and X non-negative for linear programming. So let's see. So here we've got, going back to linear programming for a second, this was our barrier for the constraints ax less than b. So we need a barrier for these constraints. And so again, for linear programming, our barrier for Rn plus, the positive orthant, was just minus the sum of log of xi's. And similarly, now I need a barrier for the positive semi-definite cone. Sn plus. So we're going to again use the intuition from Rn plus. Sn plus is a set of symmetric matrices that have eigenvalues that are non-negative. Rn plus is a set of vectors that have entries that are non-negative. I keep them away from the border by this negative log of xi. So what I really want, and I'll put it in quotes, is something like minus the sum of the log of the eigenvalues of a particular matrix. Let's stick with X. Capital X is a matrix. But what does this? The sum of the logs, remember, is equal to the log of the product of the eigenvalues. So we got a little crowded here. And the product of the eigenvalues is exactly the determinant. So this is equal to minus log det x. So this is what's going to replace that minus log in our interior point method. And again, we can now proceed in precisely the same way. I no longer have to deal with these constraints. I'm going to put them in the objective with a minus log det, not x, but appropriately, just like we had for it would be log det b minus sum of aj xj. So again, we can apply or hope to apply the idea of these interior point methods for SDPs as well. So writing this down again, I guess I did have, I squeezed everything on the previous page for no reason. We would define, let me write down the SDP. Minimize sum of ci xi subject to, I'll write it in this way, b minus sum of ai xi positive semi-definite. I'm going to define ft of x to equal the function t times c transpose x minus log of the determinant of b minus sum of ai xi. So interior point method, we let xt equal the argument of the unconstrained convex optimization problem, ft of x, and then we let t go to infinity. Now that's the idea. So we've seen some examples, that basically the two key examples, linear programming and interior point methods. This is our motivation. Let's now lay out our agenda, what we're going to need to do to show that this is a good idea, that this works. So what do we need? Let me quickly again write out what we had for LP. We had minimize C transpose X subject to AX less than B. Instead, I write down this, I have this function minimize FT of X, which is T times C transpose X minus sum of the logs of B minus AIX. So what do we need? Well, first of all, I know that I should be able to solve FT of X quickly. So step one, I need to be able to solve min FT of X quickly at each iteration. And when I say quickly, of course, I have something very specific in mind. I want to do this with quadratic convergence via Newton's method. Secondly, I need to know that I can increase T quickly. Ideally, T plus would be some multiple of T. What's the potential pitfall here? The potential pitfall is that if I increase T too quickly, then the optimal solution of FT plus could be very far from where I was before, the optimal solution of FT. And why is that a problem? It's a problem because then I might not be in the regime of quadratic convergence. Remember how we started, we're in the regime of quadratic convergence if you're already close enough to the optimal solution. And then finally, bringing it all together, I need to know how close is, I need C transpose XT to be close to C transpose X star. So these are the three elements that we need, and we're going to pick this up in the next lecture.